that things that people learn purely out of curiosity can have a revolutionary effect on human affairs. On this note, let's begin our insightful day 2 of our workshop. Good afternoon. I, Sonia Joshi, a student of TY Life Sciences, on the behalf of Department of Life Sciences and Department of Chemistry, would like to welcome you all to day 2 of Bandit Up, our 3-day workshop on techniques of chromatography. A humble request to all of you to please keep your mics on mute and your videos turned off in order to ensure smooth streaming of the workshop. The day 1 of the workshop conducted yesterday by Dr. Yogita Shinde was extremely interesting and filled with insights regarding the basic techniques and types of chromatography. The session conducted by her was very indulging since she conducted a very simple yet effective activity to understand the basic processes involved in chromatography. Post session, ma'am solved the queries of participants, thus concluding day 1 on an exciting note. We intend on extending the fun filled and educational events on day 1 to the second day of our workshop as well. Now, I would like to invite Mr. Siddharth Nakhwa from the Department of Life Sciences to introduce our resource person for today.
Thank you so much, Sonia. A very good afternoon to everyone. It is my absolute pleasure and honor to welcome our resource person, Dr. Mayuresh Joshi, for our day 2 of our workshop, Bandit Up. Sir has completed his PhD in 2017 and MSc in 2011 from Ram Narayan Ruia College, Mumbai. Sir has worked as a junior research fellow and senior research fellow in the DBT twinning project. Sir has also worked as a research analyst at Herbal Research Lab and Animal Testing Center at Ram Narayan Ruia Autonomous College. Sir is currently working as an assistant professor in Department of Life Sciences, Kishanchand Chilaram College, Mumbai. Dr. Mayuresh Joshi has 9 scientific and international research publications to his credit and 2 are in communication. His research expertise includes pharmacognosy, pharmacology, analytical method development and instrumentation, toxicology, bioavailability studies, cytogenetic, and molecular biology. Sir has presented his research works and attended over 57 conferences, seminars, trainings, workshops, online and offline. Sir has also been an invited speaker at International Symposium for High Performance Thin Layer Chromatography at a university in Bangkok, Thailand. He is also a recipient of the SBK Research Award and has also received Netravali Research Award. Sir has also been received various other awards and accolades. We welcome you, sir, for day 2 of our event, Bandit Up.
Thank you. Ma'am, shall we begin? So the host can just unshare the screen.
Yes, Mayuresh sir.
Yes, thank you so much. Okay, so guys, I hope you can all see the screen and I'm properly audible to you guys. I hope that.
Yes, sir. Absolutely. And the screen is visible.
Great. So to start with the activity, today's agenda is going to be something like this. We are going to do the first half of the of our hands-on activity for the day. Okay, before the lecture session. Okay, and then the hands-on activity has a stay time. Okay, a duration of rest, as you may say, between. So that will be the lecture span. After the lecture finishes, we will be continuing with the hands-on activity. Okay, and then observing the results and things like that. Okay, post that you will be given the post activity session. Okay, feedback form, that Google form that you all have to submit. Okay, it's very similar and quite sure you will enjoy submitting it. It's very similar to the one you actually submitted last time. And then we will discuss more about day 3 of our workshop, Bandit Up. Okay, so let us continue. Now, for the requirements, I hope you all have seen the messages and the mails that you have received. Okay, And based on that, I hope you have your requirements ready. I'll just show you the requirements that we have to take here. Okay. Now, one thing that we'll be requiring is cornstarch. Uh, let, let me just spotlight my screen for everyone. I hope my screen is now spotlighted. So one thing we'll be requiring is cornstarch. Okay, a regular cornstarch, nothing else. What we are going to do is, yesterday you all did the chalk chromatography, right? Now chalk tells you how capillary action works. How does the solvent rise? Okay, but when you want to apply this chromatograph somewhere, as you must have observed, chalk being an experimental medium, okay, a more complex medium as such, running does not happen that easily. Separation will take time. Okay, for this we come to the more advanced type of chromatography, which is TLC, or thin layer chromatography. Okay, we will discuss a lot about TLC, its difference from chalk, and then what are the applications that TLC has. Okay, in herbal products, in standardization, a bit of higher end techniques and technology also you will be learning today. Okay, so let us start with the activity. What you need to do is, as you have seen, you need to take a plain glass. Okay, it needs to be transparent because you will be reusing it for a different purpose also. Okay, I'm just switching to my mobile screen so that you can observe whatever I'm saying. And volunteers, you are requested to just follow the screen also, so that probably if anyone else is unable to see, okay, misses a step, they can then repeat that step later by observing you. The video, my screen is already spotlighted, so that it should be visible on your screen also. Okay, I'm switching to the mobile screen so that you can see what is happening in my mobile screen now. Yeah. Okay. So I've taken a small glass of, okay, which I'm using here.
Excuse me, sir.
Yeah, and now the
So I
sound seems to be
request.
okay.
Yes, sir. Yes, sir.
Yeah. Because of the double device, it was just showing up for a couple of seconds. Now it should be okay. What I'm trying to show you is a glass. Okay. We have cornstarch with us. This cornstarch we are going to be using to make a slurry. Okay. Now the slurry is to be done is very simple. You have to add equivalent amount of cornstarch, okay, into this glass, and then add equal amount of water to it. Okay, use a spoon to stir it well. I can give you a couple of minutes if anyone wants to proceed this thing. Okay, now the consistency that you're aiming for. Okay, I'll just add it. I'm switching off my video for a moment. Okay, I'll show you the consistency that you need to end up with. Yeah, I think you can all see the screen now. Okay, what you're looking at is a consistency of cornstarch which almost looks like paint now. You can observe the consistency. If you go any more concentrate, what you're going to end up with a substance called as oblique. Okay, which of course you will enjoy later. Now I want you all to just try and make this cornstarch syrup. Okay, it's plain cornstarch and just plain water, nothing else. Add it together, stir it well, and if you keep on stirring it, do not make it too concentrated or too dilute. Aim for the consistency which is sufficiently thicker, looks almost like a paint. Okay, post on chat, the chat box is open. Post on chat if you have any queries about it, or you can unmute and ask also. The chat box is currently open for everyone. Okay, during the lectures we'll be closing it again. If anyone wants, you can open your videos so that we can see what you have been doing, okay, and how you have been trying to do it. Okay, so mix it well. What you're making here is a slurry. Now I'll tell you why we are making such a thing and why we are designing this slurry. A regular TLC plate, okay, a regular TLC plate. Now a regular TLC plate, okay, is something which has a support. A support is made up of glass, or it can be made up of an aluminum sheet over which you have silica, which is attached to this sheet. Okay, this attached silica, okay, is the base, or it's called as the stationary phase. Yesterday, when you did it, you had your chalk, which was assisting the ink drop to run, right, or the ink to run ahead. Now here, silica becomes the base on which your component is going to run. But as we are trying to do it at home, okay, as we are trying to do it as a home exercise and activity, there are many things which can be separated at home, many things for which you can do a chromatography at home also. We are using cornstarch. This cornstarch will become your base. Okay, just mix it well, mix it very well, so that I will show you the consistency once again. It is almost as if it is paint now. Okay, it is not extremely sticky, but it is sufficiently thick so that it does not fall off, or simply is not too less viscous. It is viscous and it is quite thick. Once you're done, I would want you all to just put on chat if you have done it. Okay, so that we can all proceed ahead with the activity. We have got a lecture to complete also, and there is one more step remaining in the first part of this activity. Okay, please make this cornstarch and let me know if you have done with it. Volunteers? Yes. So I hope your cornstarch is ready. I'll show you the next step of. I think I lost my camera. Yeah. Am I visible, guys? Can anyone confirm?
Yes, sir, you are.
Okay, great.
Yes, sir.
Yes. Please check if it's of proper consistency. Okay, for consistency, sir, could you please check if it's of proper consistency? You can show it on video. You can unmute your, open your video also. Suchishmita, sorry for that. You can just open your video. I cannot see you yet. Volunteers, check for Suchishmita, please. Yeah, we can see you, but I cannot see the paste yet. Yes, a
I
bit
can
thicker.
see it's thin actually. Mayuresh, it's very thin. You have to make
Much thicker.
you have to add little bit more cornstarch.
So make it thicker. Make it thicker. This is Aisha. Make it thicker, please. Okay, and you also have here. I cannot see the name. Someone from BNN College, Bhiwandi. Urvi, you need to make it a much more thicker. It is quite thin. I'll tell you why you need to do it. Okay, just observe for a moment and you will get an idea why do you want to make it thicker. Okay, now this is a plain slide. Okay, what I'm going to do, I'm going to dip the slide in the mix. Okay, and it should be thick enough so that it forms a small, a very thin layer on the slide. Okay, so once I dip the slide, you can see that my slide is dipped completely inside. Okay, just observe this. I have multiple slides to show you, so don't worry about it. After I remove the slide, I'll just let it not drip. Okay, I'm switching to my back camera so that you can get the upper view of the slide. Just hold on for a moment. Yeah, now you can see from the top, this is how the slide looks like. It forms a proper layer on the slide and it does not readily dip down. You can observe this. All of you just observe, it does not readily dip down. It forms a layer on the slide. Your consistency should be this thick. Okay. Now, once you have seen the slide, you will get a better idea of what is to be done. It is to be thick enough so that you can dip something, it stays on the slide, but not so thick that you cannot dip it inside. Okay. BNN College Bhivandi, I think somebody's video is on, and you need to just add a bit more, slightly more, so that you can get a better consistency. And don't worry if it just spoils your table or something. It's just cornstarch, nothing else. Okay. The moment it dries up, you can remove it out, and it's not toxic also. That's the biggest advantage that you have. Silica gel and everything is partly toxic after a time. Okay. You can all observe the consistency once again. See, a simple way of identifying if it is consistent enough or if it's thick enough is that your spoon will start feeling heavy. Okay, you will start feeling the solution to be slightly heavier, that it does not mix well now. Okay, that is the targeted point that you are looking for to check your consistency. After which you have to just place the slide on a flat surface. Yeah, Kalavati, you can just see that you have a very uniform layer on the plate. Okay, not layers on the plate, a uniform layer on the plate. Okay, I think quite a few of you have almost got the consistency right now. Okay, once your plate is dipped, once your plate is ready, you can make multiple plates also. I want you to keep your plate somewhere flat for the time being. Okay, just keep your plates there. Just keep your plates there for the time being. Across the lecture as we go, your plates are going to dry up. Okay, it takes about half an hour at max for these plates to dry when the consistency is strong enough. Suchishmita,
Mayuresh,
your plate is properly done, I think. Yes, ma'am.
sorry to disturb you. The person who is doing from BNN college, it's actually very thick. He has to add
Yes,
little
now
bit
it is
water
not.
in this.
Yes.
The the consistency is actually very thick. You have to add just
Just slightly more water.
just
Don't add too much water.
yes. Just check now.
Yeah. I think Suchishmita has got a good plate here. All of you guys, you can see her plate. Host, can you just spotlight her for a moment? Yes, you can see that she has got a much better plate, very consistent plate, very nice. You can keep this plate slowly, very, slowly. Just don't let it get disturbed. Place it on a flat surface. It will dry up by the time the lecture is done. Urvi has also got a good plate. You can see here in one of the screens, you can see Urvi's plate. This is Urvi. You can see here her plate. Okay, so I think you have got an idea of what is to be done for the first part. Yes. So, what we are going to do today, okay, the whole thing that we are doing here, the activity that we are doing here, is that we are making homemade TLC plates. Okay. Now, this activity for the first slot, you are making it that the first time you might find it slightly difficult that the plate is, not getting covered well, or there are some bubbles on the plate, it's absolutely fine. Okay, you are learning an activity. I'm telling you this for because that we are going to have a post session activity also. Okay. Yeah, Arzu, you have raised your hand, please ask your questions. Okay, I think some problem. Yeah, right. So what we are going to do is, you are learning an activity today. The same ink, okay, the same type of chromatography that we tried yesterday. Okay, you had ink on the plate and a chalk. You can see that by capillary action, the ink would rise on the chalk. Okay, but it's a chalk. It's not consistent. It's not very thin. It's a thick medium. Okay, a lot of disturbance for the chalk to actually go through. Okay, that results in very slow growth, not so good separation also, a lot many problems. What we are doing today, we are going to do the same ink. Okay, but now it will be run on your plate, the plates that you have made. Okay, this is one of the plate which you can see. Okay, a plate which you have made, you are going to run the sample, your ink, on this plate, and you will observe how quickly it actually runs, because now the layer is absolutely thin. Okay, because we are using cornstarch, the particle size is very, very small. Okay, all of these factors are together going to play a role in actually assisting chromatography. So that tomorrow you will see the second side of the third side of chromatography, where you are going to do paper based TLC. Okay, a paper chromatography, and separation will be done by paper. Okay, so all three ways. Today, during this lecture, we'll be looking at what all is TLC used for, what is chromatography once again, okay, and what all applications of TLC can you see. So uh, if you all are ready with the plates, just put your plates aside and let them dry. Okay, we'll start with our session here, our lecture, and then we can jump back to your plates once the lecture is completed. As always, the chat box will be closed for the time being, and you can keep your questions ready once the session is cleared. Okay, we will I'll answer all your questions whichever you have regarding this uh, session. Okay, so let us just jump into the topic. The topic for today's lecture is HPTLC, and it's used in standardization of herbal products. Okay, remember, a simple chalk that you were using yesterday is not going to be able to actually provide any kind of separation or any kind of an addition or any kind of better resolution. Now these words are something which are very, very important, and as we go through the portion, through the syllabus, or sorry, not the syllabus, of course, through the presentation, you will come to understand why these words are so important. Okay, so as you discussed yesterday, as you must have gone through the data yesterday, what is separation as such? So yes, separation is like this race. Okay, river, the river is your stationary phase. Okay, on the stationary phase, all these participants that you can see on the river are your tracks or your components, your mixtures. All of these guys would stand here. They are your, this is your spotting line. Everybody is ready. The flow of the river is your mobile phase, right? The mobile phase is always going from this end of the river across to the other end of the river, right? Now all of these guys, they have their own affinities. Okay, they have their own likings with the flow of the river, or they have their own likings with the stationary phase, the things which are on this river, right? You can see some barge here, some place to get out here, another place to get out here, some trees here. So those who like the river are going to go faster. Those who don't like the river, or rather they like the scenery, or they like some intermediate attractions which are on the river, like this barge here, are going to sit here, are going to wait here. So separation is actually based on the likes and dislikes of these components, okay, with respect to what is the mobile phase, your river, and what is the stationary phase, the barges and the attractions on the river. That is it. That is chromatography. The whole chromatography can be encompassed in what you do okay, what you want to separate, the components that you want to separate. For example, say I want to separate chlorophyll components, right? You have every plant. I'm quite sure even for FI students, you are very familiar with this thing that all plants, they have chlorophyll A, chlorophyll B, xanthophyll, carotene. I want to separate that. But if I just crush the leaf, what I'm going to get is just a green substance, a green liquid thing, and I don't know what part is chlorophyll A, what part is chlorophyll B. Nahi. I don't know anything like that. So what I would do, I will just put this clump here. Okay, so let's say this is Mr. A, chlorophyll A. This becomes chlorophyll B. This is our xanthophyll guy. This is carotene, right? They are standing on the spotting line of your TLC plate. This is your TLC plate. Once you are give it a mobile phase is anything that would support the likes and dislikes of this members in front of you. It and your stationary phase can be a TLC plate, as we will see a lot of TLC plates across this presentation, or a paper, a Wattman filter paper or regular filter paper also, or a drawing paper, something which you are going to use tomorrow. Okay, it can also be done on a plain chalk, but it will take a bit of time and the separation won't be that good. Okay, but because chalk is like big particles, so the flow, the movement for this individual guys is very difficult. Okay, so on the starting line, your mobile phase starts to flow. Okay, pushing everything there. Now when you are looking at chlorophyll A, chlorophyll B, xanthophyll marked with an X here, and carotene, what you will find is that this carotene is the one to run fastest. Okay, it does not like it's polar, it runs fastest. So you'll end up seeing carotene right at the top of the plate. Okay, he will run the fastest. Then you will have xanthophyll who will run here. So based on this, you can find out that who is the polar guy, who is the non-polar guy. Likes attracts likes. So who goes with who does not go with whom. Okay, and after the plate is developed, what now you have, you started with one solution containing all chlorophyll A, chlorophyll B, xanthophyll, carotenoids, everything together, no partition. But after chromatography, now you know कैरोटीन किधर है, कितना है, xanthophyll है, A and B कहाँ पे जाके बैठे हैं. Okay, you get all four components separated. That is chromatography. A very simple, based on liking, likes and dislikes, you can separate virtually everything and anything in using chromatography. What you need to select a proper stationary phase, and you need to select the proper mobile phase. Okay, just by selecting these two things, you can actually devise a chromatographic method for anything and everything. Okay, per se, except few things which are not going to get soluble. What is the requirement? Your marker, your guys, your xanthophyll carotene, okay, these bands, these components, they need to be soluble so that they can run with the mobile phase. You cannot put rocks on or particles directly on the plate and expect that they will run. They will not. Okay, they need to be soluble in the mobile phase. That is the only requirement. Once you have everything which is solubilized, it will go. Now in your slide also, you have made a cornstarch ka slide. Now it's not great as, or not a very durable slide, but something that can show you a easy understanding. What we are going to do, we are going to apply a blue dot, a ink dot, a blue or a black ink based on what ink you have, a small dot slightly above the baseline. Okay, dip it in water and you will observe how water takes this line, takes this spot up, how it allows the spot to run up. Okay, so that it can move up. Okay, so just to recap chromatography as you understood it, simplified chromatography separates the components of a mixture by their distinctive attraction to the mobile phase and stationary phase. Okay, what happens actually? The compound is placed on the stationary phase. Okay, mobile phase passes through the stationary phase, and then mobile phase will solubilize your components. After solubilizing, the mobile phase will carry individual components a certain distance. That certain distance is defined by what is the liking of this component with the stationary phase, with the mobile phase. It carries it a certain distance through the stationary phase depending upon the attraction between both these phases. Yeah. Okay. Now we come to the this next second, or the topic of this talk. See, chromatography, you got to know what is chromatography. Okay, why is chromatography so special? Chromatography is so special because of this word here, this word which is on your screen, standardization. Now, what is standardization? Standardization means that you do once one thing so many times that it becomes near perfect, and then somebody else can easily ask you what is to be done, and even if that guy follows you word to word, he will get the same results. That is standardization. Knowing what is the exact requirement is standardization. The simplest example of standardization can be observed when you observe your mother cooking. Okay, now she is not, you don't find your mother with a weighing balance measuring how much amount of salt to be added to the sabji. No, you don't, right? Because in her mind she has standardized what is the requirement of salt to what is the amount and quantity of or volume of the sabji that she is making. So that is standardization. Knowing what is required so that same type of quality can be delivered every time. Okay, a baseline can be measured out. Okay, if I have a small bowl of sabji, then this much amount of salt is required. If I have something more, if I want to make it slightly spicy, okay, I need to add this amount of spices into it, or this amount of masala into it, whatever. That's their domain. But this is where you observe standardization, and that is precisely what standardization is. Okay, it defines the standards of how do you do things. Okay, you do things in certain way which are much faster. Okay, because they are in controlled medium, you know how to do it. Okay, the norms are already set of doing such things, so your results, they will have higher quality, and you can assure that the quality is good. Okay, whenever your mother cooks you a dish, it's not like she is not sure, she is absolutely sure it's absolutely going to be fine, and you are absolutely sure that it will be fine, because our methods are standardized. Okay, now chromatography plays a vital role in when you go to herbal medicine, when you go to pharmaceutical industry, when you go to many such things, because it is fast, it is comparatively cheap. Okay, not dirt cheap, but it is quite cheap. Okay, when you compare it with the sophisticated instruments like you that you have, it is fast. You can analyze many compounds together. You will see through the examples that many compounds can be analyzed together. You end up with standardization. Standardization is when you can set a standard. Okay, and you all need, you what you need is to improve from this baseline itself. Your quality can go up only if you follow all these standards. There is no fear of coming down, okay, failing. And this aspect is called as standardization. This is where chromatography works its best. So, how do you do chromatography? The first aspect of chromatography comes as sample preparation. You need to prepare the sample. You just cannot, I want to separate chlorophyll, xanthophyll, chlorophyll A, B, carotene, xanthophyll. I cannot just place a leaf on the slide and expect that it will run. It won't run, right? I want to crush that leaf. I want to make a transparent slurry of that leaf wherein all those pigments are now dissolved in my solvent. Okay, so the first aspect is always sample preparation, after which we go for sample application via two basic steps in between. One, I need to choose my stationary phase. Okay, I need to choose my mobile phase. We will look into each and every of this aspect of how things are done. Okay, and then there is an aspect called as pre-washing that needs to be done to these TLC players. Now, what you are doing is a very primary and crude stage for understanding purpose. But when I want to do it in an industry, when I want to do it in a research aspect, okay, I want that answer to be repeated every time, continuously, again and again. So you do something called as pre-wash. Okay, pre-wash is nothing in simple words but purifying. Okay, or clearing. This is what is pre-washing. That you let the plate run, okay, run in your solution, develop in the blank solution, blank methanol at times, or methanol chloroform at times. Okay, so that all contaminants which are based on that plate, all contaminants of water especially, TLC hates water. Okay, there are mobile phases, but you need TLCs which need to be much more specific. A simple plain TLC will hate water. Okay, then sample preparation ke baad you come to sample application. From sample application, you start the development of your plate, which is chromatographic development. Now, there are again two things that you need to be sure of before you reach to development. One, how do you design your plate? Okay, what you see here is a very simple plate with probably the space for only one band. Okay, one band, one spot. You must have seen spots. A band is also equally easier, more easier to actually get more amount of data from it. Okay, so this plate might just contain one band, one spot, but a plate can easily be 20 centimeters long. So 20 centimeter long, you need to plan your plate. कौन से track पे क्या रखे, कितने tracks run करे. As we go, as you see the presentation, as you see photographs, mark and observe the number of tracks and number of bands on every plate. It's just one plate every time. Okay. And then you need to precondition the layer. Okay, you need to make the conditions favorable for development. Preconditioning is also called as saturation, so that the chamber is now saturated with the fumes of your mobile phase which you have developed. Okay, the chromatogram will run. Once your chromatogram or your plate runs, it goes to your target point. Okay, you can evaluate it by a system or a method called as densitometry, which we will discuss in the future. Okay, as we go ahead, you can actually now identify, okay, and you can also quantify. Okay, find out what is the constituent. Now in our first example of chlorophyll A, chlorophyll B, xanthophyll, carotenoid, I can actually measure in picograms also what is the content of chlorophyll A in say XYZ plant, what is the content of carotene in XYZ plant. That is possible by chromatography. That is where chromatography leads to. It is just not a technique to put something in something and you can see some bands run out. Nahi. When you put to the application for it, it becomes a very important technique, a very simple yet very prominent technique in finding out components, in understanding what things are made up of. So you need to detect the zone. You will of course need to photograph it. You need to have a proper video documentation for it. And computation, you can report it, you can make a paper, you can publish it. Okay, so the first stage of any chromatography is sample preparation, extraction. So for preparing extract, one thing, what is your raw material? So the quality and parts that you use in your raw material becomes very important. How do you select your solvent? The nature of the solvent becomes very important. Okay, why? Because remember, separation is based on the likes and dislikes with the mobile phase. Okay, if you want likes and dislikes to be magnified, you will get better separation. If everything is very 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 similar, you will not get separation, right? So the nature of your solvent becomes very important. The ratio of the solvent becomes very important. You want that likes and dislikes to be so different that everybody won't run to the top, right? In your plate, carotene ran to the forward end. So if you don't want that, right, you want separations. For that, you need that ratio to be managed, the ratio to be tweaked if sufficiently enough so that now you can get separation. The process, you need to select what process you want to do. So in solvent selection, you need to select which solvent will give you your components of choice. Okay, if you want to extract some XYZ component from a plant, okay, you need to find out, does it come in methanol, does it come in chloroform, does it come in acetone, does it come in diethyl ether, does it come in petroleum ether or hexane. I'm saying from polarities, the highest polar to lesser polarities, hexane, cyclohexanes, and properly n-hexane. That's horrible. That's very very non-polar, right? But there are components which will prefer non-polar solutions, and you will get them only when you extract it, when you crush it with a non-polar component. Okay, the process, how do you extract? So how many times do you do it? What is the temperature that you keep it? Do you press it? Okay, or you just agitate it? Do you keep it overnight? Do you use other methods? Some extraction methods ma'am discussed with you yesterday also, right? The device that you choose for extraction, soxlet for example, we'll look at soxlet also. Okay, nature of operations, internal external factors for it. If you want to extract a volatile compound, okay, a volatile compound can be an oil. Now you cannot just mix everything, put it on a stove and let it be there at hot temperatures. Your oil will be gone. If you want to extract proteins will degenerate at high temperatures. No, not a choice here. Okay, so that becomes your selection. You want your component to come in your band first. That's target number one. Then comes separation. Okay, so what are the most common methods? You have maceration. Maceration is very simple. You take a flask or a round bottom flask or anything. Okay, put your sample into it, put your extract into it or your solvent of extraction into it, keep it. Okay, you can keep it overnight, do nothing about it. You can agitate it for some time. Okay, you can infuse it with some hot water, digest it by letting it boil for some amount of time, or you can do a decoction out of it, which the example is tea. Okay, Okay, so you boil everything together and you know that all the components of tea leaves are getting extracted in the liquid. So a regular cup of tea is nothing but an extract. Okay, so infusion hai, percolation, digestion, decoctions, or you can do a continuous reflux wherein you add your flask here. Okay, your plant material and your solvent is here, you heat it constantly, and you have something called as a reflux, a condenser up here. Okay, condenser has cold water running from here and coming out from here as a jacket. So all the vapors, they rise, fall back, rise, fall back. The cycle goes on continuously and increases your extraction capacity. You want better still, then you have a Soxhlet mechanism. You can see Soxhlet going here. Again, you have the mixture of components, your powders and solution here. Everything climbs up as vapor, goes to the condenser, the liquid then condenses. This is where your sample is. Okay, it sits on the sample, extraction occurs, the cycle completes, everything comes down, and the cycle repeats. So now you can do multiple cycles, extract as much as you can, maximum amount of components, enhance your extraction, get maximum yield. Okay, so a very beautiful technique is Soxhlet extraction. Then if you don't want to do any of that, you don't want to waste that amount of time, and you have components which will behave properly, you have sonication. Sonication is using ultrasound. So you just mix your powder and your solvent of interest in a flask. Okay, you can use a probe, ultrasonicator with a probe, or a chamber or a tank which has an ultrasonicator. Ultrasonicator is ultrasonic sound. Okay, ultrasonic sound waves are used to break this cells. Okay, jar this cells. Once the cells are jarred, all the components will simply seep out. Okay, and they seep out into your extract, and your extract is then ready, filter and use. Then you do have supercritical fluid extraction for super higher end extractions. Okay, and then you can even use a microwave. Okay, an industrial microwave for extraction. So the heating is not done directly, the heating can be done using a microwave. Okay, so these are the steps that we have done till now. We have the sample which is ready because we did extraction. Okay, we have proper sample ready. Our stationary phase needs to be selected. We don't have we have a lot of options. Now the options can be using a plain starch based stage. Okay, we are already developing a cornstarch stage at your home. You are doing that. The most common here is silica. Okay, silica gel, and this can now be added with, you can add an immuno group to it, or you can add a cyano group to it, make it more precise, make it more specialized. Okay, you can add a fluorescent marker to it. So the most commonly used silica gel plates are what is called as silica G. 60 is the pore size. Okay, fluorescence, because it has a fluorescence component embedded into it, and it will fluoresce at 254 UV. Okay, and it will be seen green colored in 254 color. We will see some plates of that ahead. So you select your stationary phase. You do a pre-washing as we discussed. You just let the plate run with plain methanol. Okay, and dry it, heat it up. Okay, and once the plate is heated, dried, it is clear, it has no impurities, it is ready for activity. A fresh box agar open karke you are using plate, you don't need pre-washing also. Then you need to select mobile phase. Okay, after mobile phase, the sample will be applied, a chromatogram will be developed. Okay, for the development you need a saturated chamber जिसमें आपका development होगा. The plate needs to be dried, and then detection is to be done. Okay, so let's jump into the steps, individual steps here. Now once the system is ready, okay, once your plate is ready, once you have selected what plates you need to use, you need to apply the sample. Now the biggest advantage that a TLC system, okay, a thin layer chromatography has, or a machine made plate especially has over a handmade plate, or a paper, or even chalk, is the requirement of the sample. You only require about zero point 0.5 to 10 moles of sample to actually get your reaction. Okay, get the separation, nothing else. That technique is so sensitive, it can separate your components in picograms. Okay, not even nanograms, you can actually end up with picograms, and it will still work. Okay, so you need a very small amount of sample. Now the simplest way is to spot a dot. Okay, or a spot as you call it. But when the spot runs, you see the spot will start running like this, and then it has to be very perfect to actually become a band. A bit tricky. The easier way, okay, if you want to overcome the problem of spotting is done as a band. Okay, so all machine made plates are also spotted as band, and you can manually also spot plates as band. Okay, these bands are going to run like this itself on the plate as it goes up, giving you a better separation. What all can be used for plating, for spotting? You can use simple capillary tubes. Okay, simple glass capillaries which you have in your lab also, you can use them. Okay, easily available stuff. Or you can use microbulb pipettes. Okay, micro syringes. Now these kind of syringes are what are most preferred for a machine made spotting ends. Okay, or you also have something called as an automatic spotter, the high end of the instruments. So these are your capillaries. Okay, a Linomat 5, the latest end spotter here. You can see the syringe being applied here. Okay, attached here. The machine uses nitrogen gas. Okay, to pump the syringe down so that very measured amounts of precise bands can be made on this plate like this. Okay, and then you have an ADC sampler or an automated sampler applicator or an automated applicator where the whole thing can be done by the machine, and your samples are actually kept here in small vials. The machine itself comes here, uses the syringe to pick up the sample, goes to its place, and as per the instructions will make bands. Okay, how do you select the mobile phase? Now if you have understood a bit of what we were discussing for 2 days, you must have known that mobile phase is to be selected based on what components you want to separate. Okay, they need to have, some of the components should like the mobile phase, some of the components should hate the mobile phase. Only then all of them will not run away on the plate, right? The components which like the mobile phase will run with the mobile phase, go up ahead the plate. Okay, those who don't like the mobile phase will stay back, and that is resolution. Okay, that is separation. So mobile phase, its chemical properties of the analytic and the stationary phase factors are to be considered while selecting mobile phase. A trial and error method is the most easiest method to develop a mobile phase. The better than that is own's experience or literature survey. Once you have done chromatography for a few years, you have a guess or a better idea of what mobile phases will work with what compounds. Even then, you need a bit of trial and error, or more better to call it as R&D, research and development, to actually end up with a good mobile phase. Okay, so a normal phase, the stationary phase become polar, and the mobile phase is non-polar. If you are using the opposite, it will be the opposite. A non-polar phase के लिए a non-polar stationary phase, the polar phase will be the mobile phase will be polar then. Okay, and then you can use a twin trough chambers for development. Now I'll show you a photograph of a twin trough chamber also where the plate is developed. Today you will be developing your plates in a glass. Okay, I hope all of you have a bit of glass and of course a bit of water that you will be requiring once we reach that point. Okay, so mobile phase selection is very important. Here what I've placed for you is an example of how different mobile compositions affect the band resolution. Okay, so it's a test die. Okay, it's a test die sample, 2 3 colors. Okay, and the mobile phase from number 1 here goes on increasing till number 8 here. Okay, in concentrations wherein you have hexane full with 0% ethyl acetate, then 5%, 10, 15, 20, 30, 40, and 90% ethyl acetate, and you will see that 0% nothing goes up. Okay, nothing is going up, there is no ethyl acetate, hexane goes up and nobody goes up with hexane, right? As the mobile phase runs up with hexane, nobody goes up. That simply means that no component in this mixture likes completely non-polar component, it doesn't like it. Now if you, when you have a small amount of ethyl acetate added to it, ethyl acetate is more polar. Okay, when you compare it to hexane, it is much more polar now. When you have a bit of ethyl acetate, 5% ethyl acetate in pure hexane, you can see 3 bands getting separated here. As you keep on increasing to about 20%, okay, and 30%, you can see now that the separation is very good, especially in this. You can see that they are in the middle of the plate, equidistant from the top and from the bottom. and very well resolved 3 dyes. So that is a very good composition. That is how you select a mobile face. You start with something, a pure line, okay, keep on changing it till you end up with a proper mobile face, which will show separation in the middle of the plate. Okay. So based on similar, once you have the mobile face, you need to define how much we want to run. Okay. So this is chamomile oil, which is using HPTLC silica gel G stationary phase. The mobile phase is ethyl acetate or toluene, which is standardized at 5:95 composition. You can see this plate is allowed to run only 3 centimeters, 4 centimeters, 5, 6, 7, 8. You can see as you go up above 7 centimeters for this plate, for this example, please understand that I am not telling you universal rules. Okay, I'm telling you how development occurs. So when you want to develop your mobile phase for your plant sample, your results might be slightly different. Okay, so when it is allowed to grow to develop to 3 centimeter, 4, 5, 6, 7, 8, you can see at 6 centimeters, the separation is the best here. You can see this thin bands to be separated. If you go higher, the bands become blurry. If it is lower, you do not see certain bands coming up. So then 6 centimeter development becomes the easiest way. By just making the lens equal to 6 centimeters, you can see even in this kind of an observation, this plate, the 6 centimeter developed plate, shows best results. So that is how you conclude with a mobile phase, how you select your mobile phase. Now, what are the effects of the mobile phase? Okay, again our test die. Again our test die, 4 plates. Okay, you can see this is A sample. In A sample you have hexane and 15% ethyl acetate, which was used as mobile phase. 4 of them will sit here, the 5th one goes here. Now I change ethyl acetate to acetone, and you can see that this pink colored band here has moved up. The rest is pretty much the same. But now if I change the whole type of compound completely from hexane, from acetone to isopropanol, okay, you can see a drastic change here. This band goes up, this band goes down. Okay, these two guys come very close to each other, not favorable. And then if I convert everything to pure chloroform, you can see the change occurring again. So using these compositions, you will finalize your mobile phase. So what all we did, we took one simple component, found out what are the affinities, what is favored, what is not favored. Okay, then we decided to for standardize. This is standardization, wherein you decide what is the perfect for your mobile phase, something which you can repeat again and again and again and again and again, and even then you get the same results. Okay, so first we decided what compounds to be selected, then we decided what should be my length of development, and the third thing, we are deciding what is the perfect compound here. Okay, by all of these things, now we can have our mobile phase as final. Okay, now we also discuss something called as saturation. Now whenever you want a plate to develop, okay, in your chamber, this chamber development needs to be better saturated. The environment needs to be filled with vapor. It's very simple, it's not that complicated. You have a chamber here. Okay, you will put your mobile phase down in the chamber and then cover it up with a lid. Okay, keep it like this for 20 minutes at least. What is happening, you have a filter paper on one side of this paper of the chamber. Okay, the vapors start rising up from the mobile phase. Many of the times mobile phase is organic. So if you have, for example, acetone, so acetone vapors will start filling up the whole chamber here. So whenever I actually put my plate inside, my development becomes easier. Okay, the proof for this is a plate which was developed without saturation. Okay, no saturation here. The second plate with a lid now. Okay, it's not open anymore, it now has a lid, so vapors are not escaping that easily. And the third plate with a lid and a filter paper. Okay, the credits of many of the images that you will see through the presentation, they are written at the bottom of the slides. Okay, so Dr. Sunita Jalajan is my guide, so with whom I have worked in herbal research lab for all these plates. Okay, so it's from during those research dates that I've picked a few examples for you here. Okay, you can see the plate developing and the effect of saturation, which is very clear. That's why always, today you're just using water which won't evaporate, but in the future whenever you do chromatography, see that you put a lid without fail on your chamber, okay, and you don't move your chamber, because you want that saturation, you want that pre-saturation effect, and you want a proper separation. Okay, so what all can be used for development? This is what I was talking about when I'm saying twin trough chambers. Okay, you can see twin troughs because उनको दो खड्डे होते हैं ऐसे. So you add your mobile phase here, add your mobile phase here. Okay, you place a filter paper on one edge. Okay, saturated filter paper. So यहाँ से भी vapors will come in, vapors will rise from the mobile phase also, and you can place your plate. Okay, and the opposite end like this. You can place your plate. I'm looking from the opposite side. Okay, you can reverse it up. So this is the running side of the plate, this is the back side of the plate. Okay, the plate runs because of the vapors, the plate runs much more easily. So here you have then ADC and automatic dipping chamber also, horizontal development in twin trough chambers. So after chromatography, after my plate is ready, what now? Okay, there are three aspects to what's now. One is detection, then documentation, and third is measurement. Now in detection, UV is always the first choice, because remember what we can see with our normal natural eyes is very, very small in comparison to what all is available. Okay, there are many compounds which are perfectly invisible to us, we cannot see them. Okay, so many of these compounds will be visible under UV light. So UV becomes the choice of interest, an easy choice. Just observe things in UV. If the compound fluoresces, okay, you observe it in 366 nanometers. Okay, you will see some plates at this also. If the compound does not fluoresce but it can take up UV light, okay, it is called as quenching, and you will observe this compound behind green light, which we will also see. Okay, so it's a non-destructant method. Spots with fluorescence can be seen at 254, okay, short wavelengths, or at 366 also. Spots who do not fluoresce can be seen against the silica gel G green looking plates ke upar. We will see those examples. Now, when the spots are not visible in UV, if the compound is still not visible, I want to see the compound. Okay, optically the compound is not visible. Direct plate पे देखो कुछ नहीं दिखेगा. Okay, then what I do? I do something called as derivatization. Derivatize means, in simple form, you react. Okay, make those compounds on your plate react to acids and compounds which can give color. Yesterday, the example that you observed for derivatization was iodine. Iodine was assisting, okay, in visualizing the compound even when the compound was not visible. So iodine would react, okay, and bring the compound in the visible spectrum so that it can now be seen, right? So derivatization is just enabling visualization. Okay, when the compound is invisible, you react the compound, make it visible. It can be done before. Most always it is done post chromatographic derivatization, so post after the development. So you can simply spray, but spraying is though easier in a lab condition, it is not that preferred. The most preferred method is dipping, but dipping may you require more amount of solvent. Okay, spraying may 25 ml of solvent will be enough for the whole class. For dipping, the whole chamber, a chamber like this requires 300 ml of this solvent. But when you dip the plate inside, it is uniformly derivatized. Okay, so everything becomes colored, and then you want to measure it. Now measuring is done against background light. You want to photograph it, which is using a camera. So you have photo documentation units which can actually bring photo, take photographs. You will see some photographs ahead which are taken by such a camera. So just to recap everything, I want you just to see a small clipping here, okay, wherein we will recap everything that we have completed till now and then go for examples. So thin layer chromatography is what we have been studying today. You have a chamber here, okay, which is filled with mobile solvent. Your mobile phase, which is selected with so many standardization aspects. You select your mobile phase, you select your TLC phase, okay, the stationary phase here. Many a times an alumina sheet which has silica gel on it, okay, which is attached to it, silica attached to it. From the base, 1 centimeter, you draw a small line. That is your baseline. Even today, when you are going to spot your plate, when you are going to add a drop to this plate, see that you add it at least 1.5 centimeter above the base. This is the base of the plate. Okay, in the center, you just drop a small drop of ink. Not now, later. It runs very fast. Don't worry about it. Okay. Now you're just adding one drop of sample. There are 4 samples as you can see in this animation. So you just add a drop of sample, very minuscule drop, 1 mm or 2 mm drop of a good concentrated solution is more than enough. Okay. You add everything to your plate. Your mobile phase is saturated in compound. You put your lid back, or else of course you will not get the good amount of separation and stuff like that. And then your mobile phase starts to run. Now when the mobile phase is starting to run, there are 2 things which are happening here. Okay. This is the mixture of compounds that you can see on your screen, okay, coming up. And out of them, few of them, the orange one stays down. Okay. If I'm not wrong, yeah, the green one goes up. So the green one likes the mobile phase, the orange one does not, likes the stationary phase more. Right. With the mobile phase, the green one goes up. There is a second type of understanding that you can observe. If the compound is polar now, okay, the phase is polar, the mobile phase is non-polar. Okay, similar to a silica gel G compound. Okay, a polar one now. Now what happens? You can see again the compounds running up ahead. The results become reversed. Okay, because of their liking and disliking, the green one being non-polar goes up with the system. Okay, and eventually your plate will rise up. You want to stop the plate rising from a certain point. You don't need to eventually let it go. Okay, you mark out your topmost point. Okay, that becomes your solvent front. That is the point where your solvent has run. Your solvent ran till that point. Then you want to dry your plate. Okay, at the moment you have just kept your plates aside. You observe your plates must be properly dry now, and with a proper layer on top of it. Okay, after the plate is dried, you can directly just visualize it under UV radiation. So observe, it's a UV chamber. Okay, at the moment you can see that nothing is visible on the plate, but when the plate is put under UV light, you can see that certain spots become visible on the plate. Okay, so there are slits for marking in UV visualization chambers, when you can now use a pencil to just mark the plates wherever the bands are, and then determine the retention factor. Okay, or the relative front. Now if I want to still see the bands, okay, because I have not seen the bands as such, so for aromatic compounds I can use an iodine. Okay, for amino acids, the simplest derivatization is ninhydrin. Okay, for any compounds that can be oxidized, you have potassium chromagnet, potassium permanganate. Okay, or aldehydes, ketones, alcohols, you have vanillin. Okay, terpenoids, saponins hai, so you have 10% methanolic sulfuric acid, you have anisaldehyde sulfuric acid, and so on and so forth. All these are derivatizing agents. One derivatizing agent that you have already seen yesterday was iodine. Okay, so you select your derivatizing agent of choice. If you are working with amino acids, you just spray the plate with ninhydrin. Okay, when the plate is played, you want to heat the plate. Derivatization ke baad, you need to heat the plate. Okay, many a times that heating can be 120 to 140 degrees also for a very short amount of time. Now you calculate the developed distance of your component and the component of your solvent. You divide it, find the RF factor, and this is what is the most important aspect of TLC that you see here. You can see that all these components, sample A has all these components. Then this track here, A track, B track, C track, has individual components. Now, chromatography has a special ability. That special ability is all compounds, even if they are mixtures, will behave with their own rule. Okay, their affinities will not change. Even if they are in a mixture of 100 compounds, their affinities will not change. So, because affinities do not change, their RF values will not change if the mobile phase and all other components are remaining the same. These changes will not occur. Okay, so you can see that sample A has ran up exactly to the amount of this orange band here. Okay, B till here and C till here. So if you calculate the RF, you get 0.23, 0.41, 0.88 as the RF. Okay, based on components, based on your stationary phase, you can easily find out if it's a polar component or a non-polar component. And then from your sample also, you can see that there is one more band which is of similar color, same RF on the same plate, it must be the same compound. So TLC will help you detect this compound, okay, and confirm that it is the same compound. These compounds are marker compounds. Okay, so you have alkaloids, you have terpenoids, you have specialized biomarkers which can be found from these compounds. So this is an example of a biomarker which is found at the same RF, and now you know that yes, this green colored compound is present in my sample. This blue colored compound is absent in my sample. Okay, this orange colored compound is present in the sample because it's showing the same color and the same RF. Okay, no difference. Now, let us take some examples in some amount of time and then we can jump back to your plates. I'm quite sure your plates must be already dry. Okay, don't move them, let them dry. Okay, let them dry. So even if the plate is slightly wet, you may, moving those plate immediately, and that the layer that you are forming, if it is not dry enough, can just fall off. You don't want that. Okay, so let it dry. I'll show you some plates, some of the earlier researches that we have conducted on chromatography. And what I want you to see is that chromatography, it is highly applicable, it is highly useful, huge amount of applications. It is very beautiful. Okay, there are many beautiful things that you can actually find on chromatography, and the compounds then look much better. Okay, so one example here taking is of these two plants. The upper one is a mangrove Avicennia marina. The lower one is a mangrove Soneratia petala. Now, if I just give you the powder of these mangroves, it will be impossible for you to tell me the difference between these two mangroves because the powder does not have a distinct smell as such. It is almost brownish in color, both plants. So no distinct color difference as such, no texture difference as such. It's impossible to tell them apart. That is where you have chromatographic fingerprint which comes into play. Okay, the one of the most important uses of chromatography, TLC especially, and HPTLC, is fingerprint. Okay, so the mobile phase that I'm using here is toluene methanol ethyl acetate 9 is to 1 is to 1.2. Okay, a 60F254 HPTLC plate. Two types of derivatizations are tried. You will see the photographs. Okay, and green plates are the plates which are visualized in 254 nanometers. Okay, ultraviolet. Dark blue plates that you will see, blackish blue plates, these are 366 may observed plates in dark ultraviolet, okay, UVB, and then 540 which is visible light. So these are plates before derivatization. You can see that the first plate, the green plate, does not show any bands. So one, both these plants do not have any such compound, which is not more compounds which are quenchers. Okay, but there are compounds, you can see the second plate, which are fluorescent, because under fluorescence all these compounds are very nicely seen. You can see some of the bands are common, but there are some bands, for example this band here, which is very individualistic. Okay, it is seen in the second plant itself. They are only the Soneratia petala plant, not in the first plant. So now, even if you have two powders which are very similar, no idea what it is, and you can run this plate. Okay, do the same thing, use the same mobile phase, use the same you don't need derivatization here at all. Just run the plate in this mobile phase, you will be able to tell which is the powder, which is the plant. That is the biggest advantage of chromatography. Okay, then I want to see many more bands also, because always many more bands, I told you, are not visible easily. So I will derivatize this plate in 10% methanolic sulfuric acid, and now the same plate, this is the same plate, not a different plate, the same plate under 366, you can see a very different set of bands. This band, it's a terpenoid called as ursolic acid. You can see that ursolic acid is present in Avicennia marina also, Soneratia petala also, but here it is more. So quantitation is possible. Okay. In visible light also you can see that this plant, the second one, has few more bands in this area. This band in the first plant is very different. So these are identification points which can be observed in this plant. This is second type of derivatization. So what you see on screen at the moment are called fingerprints. Okay, fingerprints, because if I give you these two plant powders, if I tell you what to do, you will get the same result always. Okay, that's the capacity of TLC. That is why it is held as one of the most sought after techniques when it comes to standardization and herbal medicine and pharmaceuticals and so on and so forth. So it's very important to understand does not only on another plate from a book called as Reach. Now Reach and Ike Reach, and these guys are the topmost leaders in chromatography at the moment. So what they have come up with is the fingerprint of a mushroom. This is the mushroom Ganoderma. Okay, fingerprint of Ganoderma. You have 16 tracks on the plate. 1 to 13 is Ganoderma lucidum collected from different locations, derivatized with sulfuric acid, and observe the plate. Now you can see that every location there are similarities, there are differences. Okay, this is useful to understand what is the variation in Ganoderma. Okay, what type of the last three tags are only the mycelium of this mushroom. You can see that they show the presence of this band, which is very different, which is not present anywhere. This band here is again very different, not present anywhere. Okay, suggesting that even if I make a powder of Ganoderma, please remember Ganoderma is highly medicinal. Okay, so there is a lot of medicines which does have Ganoderma as one of their ingredients. So instead of using the right powder, if I want to cheat and just add some mycelia, I can be easily caught by chromatography. Another example is another a plant which is very famous in homeopathic medicine, which is belladonna. Okay, Atropa belladonna, which is atropine. You have three alkaloids here: atropine, then yosamine, okay, and then scopolamine. These three alkaloids you can see here in different derivatizations. These three alkaloids have been targeted from the Atropa belladonna plant, okay, which was collected in different locations. A simple mobile phase. This first plate here is non-derivatized plate, okay, at 264 nanometers. Second is also non-derivatized. You can see that not many bands can now be seen, okay, especially the marker bands of track 1 and track 2 are not visible. For alkaloids, whenever in the future also you want to do an alkaloid TLC, drag and drop is one of the most sought after derivatizing agents for alkaloids. Okay, make a drag and drop solution. Bismuth nitrate and potassium iodide are two components which are required to make drag and drop. And now observe this. It easily tells you that all plants have this one band which is actually of atropine and yosamine. Okay, a bit of component of both of them present in both plants. This is the second component of yosamine, and you can see it to be present here also. This is the third band here of scopolamine. Okay, now scopolamine is not clearly visible even in drag and drop, so you do a double derivatization. You react it with sodium nitrate. Okay, NaNO2, it reacts again, and now you can see this. So this is called as detection, okay, using derivatization. So we saw simple plants, we saw alga, we saw medicinal plants with alkaloids. Now another very a common thing that is green tea. Okay, so green tea, you have Camellia sinensis, another beautiful work here. Okay, you have all major class of phytoconstituents which are detected from this four varieties of green tea. You have standards here, okay, of these components, the actual green tea, okay, the green tea extract here, and the commercially available product. Please observe that the commercially available product does have certain things which are properly missing, okay, and chromatography never lies. Okay, it's absolutely true always. As long as you have the original plant material here, you will never get an odd answer. Okay, it's always true. So in flavonoids, the commercial has something missing here. Okay, the second plate here is for alkaloids in 254 nanometers. You can see another missing dot here. Okay, then you have amino acids. You see some amino acids which are added up here, or some additions here also, suggesting that there might be some mixture in the commercially available product. You have polyphenols also. The first three, this is the standard track, the green tea, the green tea extract, and the commercial. You can see that the commercial track the band intensity is low. That means that probably the quantity which is actually added, except from the excipients and adulterants, might be less. So one of the use of HPTLC is to detect adulteration. Okay, to find out if whatever I claim is true or not. If I tomorrow I give you some sample and tell you that this is sample of some say mango tree, okay, the very common tree. So a powder of mango tree, but you need to confirm it, right? If you're going to take it as medicine, you need to confirm it. That confirmation can be done by using techniques like this. Okay, So this is another example of Tulsi. I'm going to send you the presentation so that you can all watch the photographs more neatly later also, no issues. Now, this HPTLC can also be used to just standardize solvents also. Okay, just to find out if the solvents are okay, if everything is correct or not. Even for that purpose, an HPTLC system can be easily done. Okay, so an example is again with the first plant example that we started, Abyssinia and Sonaretia, to find out where is the extraction better. Okay, a simple mobile phase 254 में कुछ नहीं दिखा, 366 में ज़्यादा कुछ नहीं दिखा, so you need a derivatization. Derivatizing it with 10% methanolic sulfuric acid, and this is the plate. Okay, in this plate of mine you can see that the first track here, track 1 and track 2, is just distilled water and hydroalcohol, does not show too many bands, यानी extraction अच्छा नहीं हो रहा है. Okay, that can be easily concluded. Plate 3, plate 4 is methanol, shows very good number of bands. Ethanol shows good number of bands, and then comes ethyl acetate. You can see some extra bands in ethyl acetate also, suggesting ethyl acetate is the best for this plant. Okay, then you have toluene, जिसमें थोड़े missing है. Nxane, again a few bands are missing. So I know that ethyl acetate is one of the best for this plant. Now similarly for the second plant, the track number 8 here is standards, running standards with it. Okay, track number 8 is again distilled water and hydroalcohol is not showing great amount of components. I don't want them because I want maximum components. I want the plant to be medicinally proper, right, of the proper class. So I try with ethanol, methanol, अच्छा है. Ethyl acetate shows the presence of more bands, more components. Even this band is much brighter, suggesting ethyl acetate is again good for this plant for extraction. So, and this is the plate. The same thing after visualizing it at 254, you can see that what we observed under 366 does pan out even in 254. Track number 5 shows better promise. Even here, track number 11 shows better promise. You can see a band which is much more prominent than the other two. Here also the same. Here you can see a band which is absent, so it is extracting more components. Okay, so HPTLC you can use for identification, for authentication of a plant sample, identifying if it is correct or not, identifying concentrations. Okay, identifying phytochemical groups, major group of phytochemicals present है, absent है, वहां से शुरुआत. Then you can find out if something is adulterated or not adulterated. Now you can find out if extraction is actually occurring or not occurring. These are all manual made pleats. Okay, this is not a machine. This is spotted by a machine developed by hand. So you do get lot of bands and lot of things with HPTLC that can be done. Okay. The next use of HPTLC is to understand regional type of variation. The same plant, okay, I tell you that there is some plant which has some XYZ medicinal property. Now I need to know if the same plant, if I find it from Mumbai, and the same plant if I take it from say Sundarbans, does it have the same property? Properties will change. How will I know what is the deviation? How much change is there? Change is defined with the content of these markers. These are phytoconstituents, chemicals from the plants, right? So I can detect this differentiation. You can see the plate in front of you. Okay, this is the same mangrove which was collected from 10 different locations across Maharashtra. Okay, and also from Uttarakhand, West Bengal, Sundarbans. Okay, and then everything is set inside. Now you can see there are certain variations which are observed, right? So you have track number 3 and 4, that is the Thane and BKC, wherein some other components are also present here. I am looking for these 5 components especially, right? Because I have a marker set that is ready here in this example. If I don't have a marker set, I will always go for the area which gives me maximum amount of components. If I'm looking for a marker set, I will look at what is the maximum marker content. You can see the plate can be now densitometry. You remember the word scanning, densitometry. It converts this whole photograph, okay, into a graph like this, okay, which can be measured, quantitated, calculated, and you can get a graph. In the graph now you can see that the content of these 5 markers is found to be maximum in Airoli. Okay, so this is another importance, another application of HPTLC. So sab ho gaya, adulteration ho gaya, quantitation ho gaya. Now to find out regional variation and use it to find the better region. So compare plants, the same plant, same material, compared across to find out which is the better one. Okay. Similar things can happen with traditional formulations also. These are a few examples with Arkavati, okay, Lavangadi vati, and the marker, standard marker called as piperine, which is the medicinal property of this vati. If you have ever eaten Lavangadi vati, it's available OTC, okay, over the counter in any shop also. Very good for cough and very good for throat. It has a pungent taste because of piper, and that piper, the taste is because of piperine. So you do it, you analyze it. In this current study, what we did was make it in house, both these components, and compare it with what is available on in the market. And we found that the in-house formulation actually has a slightly higher content of piperine. So again, this is called as standardization or control, quality control. So assessment of quality can be done using HPTLC. Okay, another use of HPTLC. This is your famous regular Trifala Churna. Okay, Trifala Churna, three plants, Amla, Beheda, Harda. Okay, with the common Trifala. You can see that these bands from Harda can be seen here. Okay, this band from Beheda can be seen in the formulation again. Okay, from Harda, also some bands have popped up right in the formulation again. That can be used to find out if the Trifala is actually made up with three components or not. Okay, another use, and this also use is called as quality evaluation. So you evaluate if the quality of the sample is good or is it bad. Okay, same an example for Unani medicine. So Sulfurphase diabetes Zulabe is one Unani medicine which is very good for diabetes. Okay, but is it proper or not? Just take all the ingredients. Okay, take the actual Sufuf, plot it up, find out if things are there or missing. Okay, another example you have, so it's not restricted to foreigns also, you have orchids. So this was a project that we did with Nehu Shillong, okay, based on identifying orchids, because orchids are slightly confusing in identification. So a simple TLC methods, okay, were used for identification purpose of a plant which is not, which is getting confused with two other plants. So there are 5 species of orchids in that location of Dendrobium class of orchids. You have Muscatum, Fimbriatum, or Chrysophyllum, Chrysotoxum, okay, and Nobile. Now they are getting confused there because the orchids, only when they flower, these orchids are actually, you can differentiate with them. When they don't flower, they absolutely look the same. So how do you identify? You identify using chromatography. Okay, another usage. Not restricted to biocomponents, biomarkers. This is chromatography or TLC of amino acids from lichens. Okay, dry the lichen, powder it up, find out if it's present or not. You can see the lichen track here. Okay, this is the first band presence, this is the second band, and there's a very faint third band present up here which cannot be seen in the photograph, but which could be detected in the sample here. Okay, and this is called as spectra matching, which confirms that the band is present or not. Another application. So now chromatography is not restricted to all regular compounds also. You can virtually take anything. You just need to develop a proper mobile phase and a proper stationary phase, and of course detection. Another odd matrix, we took plants, okay, all good plants with proper activities, mixed them up and made a herbal oil. Just extract it. A very different kind of extraction needs to be followed, and you can do a PLC of herbal oils. You take the same herbal oil, okay, and spice it up with a till oil. Okay, till oil is again medicinal. Put it in the herbal oil, compare it. You can find that the content of marker is increasing. So all these kind of bases, all these matrices can also be taken. TLC is not restricted to even this. You can have, you can do human plasma can also be detected on TLC. Markers from plasma can be detected, markers from blood can be detected, proteins from the system can be detected, some medicine you took inside can be detected. Okay, a TLC system can be worked on it. Another example of a formulation, Pushanuga Churna, which is available by many. It's a 25 ingredient formulation done by my ma'am. Okay, and it's available by in many by it's marketed by many people. So under a project, what ma'am has done is ma'am has collected all those plants, all 25 plants and another mineral in it, mixed it, prepared a formulation in the lab, and then compared it. Now, when she compared it, it was very evident that you can see that this is the homemade the in-house formulation, look at the number of bands in the in-house formulation, and look at the other tracks. You can see that the tracks are visibly empty, suggesting that probably the ingredients used are not of that quality, or probably some kind of adulteration has occurred, some kind of ingredient damage has occurred, and so on and so forth. So another use of TLC is this. Okay, so just to take an overview, because we are almost at 6 and we need to complete our activity also. So just to take an overview of what is there, factors affecting HPTLC include the type of stationary phase, okay, the mobile phase, then you have the layer, the thickness of the layer, the temperature at what everything is happening, mode of development, amount of sample that you are using, and dipping zone, dipping areas. All these things will also matter. In applications, just to give another a feedback of applications, I am quite sure you have seen many applications and noted down quite a few at least. So pharmaceutical industry is one of the prime areas where TLC and HPTLC is used. Okay, quality control, identification, purity testing. Food analysis is again a very important factor. Remember, food color testing is a very prominent area where TLC is used. Clinical applications, metabolic studies. Simple example is you take a crocin, right? Now the doctor advises you that you should not take a crocin within the next 6 hours. Okay, why is that? Because crocin remains in the blood, okay, up till 4 hours, after which it goes out. At 2 hours it's maxima, at 4 hours it tips down and goes out completely. How do we know it? We know it because of chromatography. Okay, the crocin is, the patient is allowed to eat a crocin, the blood is drawn at different time points, separated out, okay, extraction is done, and chromatography is done. The marker, the marker or analyte that we are looking for is acetaminophen, that is which is paracetamol. Identified, you know when at what time was paracetamol in what quantities in blood. Another application for clinicals. Industrial mein process development optimization, I think ma'am explained that part also last time, yesterday, when the use of chromatography in these aspects. Also you have forensics. Poison investigation is an example for forensics uses. Biomedical uses for separation of a range of compounds. Okay, environmental analysis, pesticides in drinking water purity, potability studies. Then you have cosmetics, so hydrocortisones and all these products which are, remember, even a simple component like Fair and Lovely. Okay, does Fair and Lovely actually contain the component that the company promises? That can be tested. Put it on chromatography, you can test it. Okay, you have natural ingredients, plant products, glycosides from some plant, piperin from here, digitoxin from digitalin, then taxol from Taxus baccata. You have so many plants. Mangifera, say mangiferin from Mangifera indica. Okay, mimosine from Mimosa pudicas. N number of plants have been tried and tested on chromatography. Go online, check. You will get a huge amount of data for this. And of course, fingerprint analysis to find out identification, authentication, prevention of adulteration, substitution prevention, analysis of blood, drugs of various kinds, bioavailability, bioelimination studies. That's a bit on top, but these are also the applications for chromatography. Okay. Now there is a difference. Please understand that HPTLC and TLC is not a difference of an instrument. Okay, it's not like if you are using an instrument that means you are doing HPTLC. Nahi. Even TLC can be done with an instrument. The difference is in the plate, is in the stationary phase. HPTLC is a very high quality of stationary phase which is used, and regular TLC is a very similar looking stationary phase but with a different pore size, different uniformity, and of course cheaper. An a TLC box will cost you around 5,000. HPTLC box costs you 35,000. So that is the difference. But of course, a TLC gives you 100 units of separation. HPTLC gives you 1,000 units of separation. It's much more better. So that is the difference, and that is the advances that we are looking at. Okay, these are the applications of TLC that we are looking at. So just to conclude the session, there is an activity which we will be conducting tomorrow. Okay, once the session starts, before the hands-on the project actually begins. Okay, there will be an activity which is a brainstorm. What you have to do as a homework, as a post-event activity for today, is rattle your brains a bit and find out, think of all the applications of TLC that you can think of. Google out, search around, develop your ideas. Okay, it is your ideas, your project, your concept, your execution. Okay, In the feedback form, which will be shared to you shortly after the QA session, in the feedback form, there is a special space given for you to write that ideas. The feedback form closes at 9 in the night. Okay, so you have time, you have 3 hours. Sit down, think about the idea, come up with some good ideas for tomorrow's brainstorming session. We are going to discuss your, we will be getting your feedback forms, we will be getting an idea of your ideas, of course, and the topmost ideas, we will be discussing those ideas. Okay, so the sky is the limit. I think what today's presentation was on, why it was there, was to tell you that sky is the limit for this whole thing. There is no limit. You can think of an idea, you can think of an application, all the ideas that you think of, you can write in the feedback form, and let's see what all can you cook up with. Any great idea, and of course that will develop into a project, and it will develop into a post event activity also. Also, we will be concluding the session with our TLC plates and our activity. Okay, post QA session, and then we can conclude with your activity also, I think. Okay, so ma'am, shall we take the questions now, or shall I just complete the activity first? I think we can complete the activity.
I think there is no question in the chat box. You can continue with your activity. Meanwhile, they can post their queries in the chat box.
Yeah, the chat box is open publicly for all. You can post your questions in the chat box. And till then, of course, back to our activity here. I am re-switching to my phone camera also. What I want you to see is 2 3 very simple things what you have to do, and what you have to observe. Please understand, the plates that you will run, you need to take a photograph of that plate. There is a scope in the feedback form for the good photographs to be uploaded. Okay, so those photographs can be uploaded, and I think it will be very nice for all of us to just see those photographs also. Yeah.
So we'll move to the question and answer.
We will just complete our activity first and then move on
Okay.
to the question answers. Participants can write the questions in the chat box till then. Okay, so I think I am yeah, I am visible here. Now what you have to do is take your plate. Okay, whichever plate you are ready. Participants, you are allowed to open your videos so that we can continue with the activity. Okay, take your plates. You already have your ink with you. Whichever ink you have, I have a Camlin simple ink with me. Okay, a simple ink with me. What you have to do, okay, is take your dropper from the base of the plate slightly up, about 1.5 centimeter above the plate. Okay, I'll just switch on to the back camera. So if this is the base of the plate, I'm just showing you there. I'm not going to drop anything up at the moment. Just above the plate, about here, okay, I want you to drop a small drop of ink. Okay, keep the drop very small. Please do not put a huge chunk of a drop on the plate. A very small drop of plate is sufficient. Okay, place a drop of ink on that spot there. Do not place it absolutely at the bottom. Place it about a centimeter from the base. Okay, you can all do it, and then we can proceed ahead with the next stage. Yeah, now I think you can see this part. Okay, so once that aspect is done, what you have to do, take the empty glass. Remember, 2 glasses. So take the empty glass. Okay, pour in very small amount of water in the glass to the base. Okay, the idea is that when you put your plate inside, this spot should not touch the water. Okay, it should be above the water. The spot should not touch the water. क्लियर एनफ. सो उतना ही पानी डालो जो नीचे से यहां तक, प्रोबेबली अप टिल दिस साइज. ओके, here you can see the spot also. You can see itna tak hi it will get submerged. Only that amount of water you have to add. Okay, and keep the slide and everything ready. After which we'll be putting it inside. In a moment, I will also just add a small drop of ink. Yeah. So if you can see the plate, I think I can just spotlight my video for the time being. Yeah. If you can see my plate, I've marked a very small drop of ink, okay, on the plate, and my plate is ready to be dipped. Okay, all participants, you can switch on your videos also. What you have to observe is this: once the plate is dipped inside the chamber, I will repeat one small instruction once again so that fiasco doesn't occur. Okay, already Sushmita can see your plate running. That is good. See that the plate should reach the water, but it should not get submerged in water. Okay. Yesterday on chalk, you could not see the actual running aspect, but now if you observe how it runs on the a plate which you have created at your home. Now, for your post activity, you can use this concept also, and I mean come up with n number of activities through this concept. Yeah. You can all unmute. You can show what you have done. You can see on my screen the band, which is the track which is rising. Now, currently, it only has blue colored ink. Okay, because it's a concept, it's a method that you are being taught. What all can you do with this? You can mix 3-4 color of inks, try to separate them. Mix 3-4 watercolors, okay, try to separate them. See how they react with water. Okay, then you can, okay, and what all can be done? You can take food colors, take few food colors, mix them well, use the same TLC method, try to separate them. Okay, you can see that the plate will keep on running as it goes up. After a certain amount of time, that's enough for me, say. So I can remove the plate, and you can easily see that the plate has run considerable amount of distance. Now can actually see that there are, this is the bigger band here. A small amount of different coloration is also coming in the middle. Okay, probably some impurity or something right in the ink that was observed. Yeah. The second aspect of the post activity that we are going to do, one is tomorrow's brainstorming. Okay, and then we will be discussing of another post event activity tomorrow. So this activity, please complete it. Okay, in the feedback form which will be launched on the in the chat box soon during the QA sessions, you do have an area where you can upload your photographs. Okay, display those photographs for us. Tell us how you have come up with the activity, how your plate was created, and how what reviews you would like to give to your activity, and then of course your ideas. Your ideas, you can think of your ideas, come up with some brilliant ideas which you can take up ahead as projects also. I'm quite sure after the brainstorming, you will be ready with few projects. Okay, HPTLC is something that you can do wonders with. And just shifting to the main camera. Yeah. So I think that actually concludes the activity session also, and our lecture also. The session is open for Q&A. If you have any questions, let the plates run. Keep a marker on the plate. Let it not run too much. I can see Sushmita Hushal with a quite a lot amount of ink that you have added there. You could have added a small amount of ink, probably a smaller dot. Sakshi, I can see her plate also rising here. Okay, Urvi shows, yeah, her plate is also rising, I think. Archana can, yeah, her band is very small, very nicely spotted small band, and you can see that also rising. What is observe the basic observation that you must have done is yesterday when you when you use a chalk to understand capillary action, because the chalk is a denser medium, or rather a thicker medium. Okay, there is a lot of area that the ink has to travel to actually go ahead. But how did we reduce time? We had a covered, we had a stationary phase which is now very very thin. Okay, if you can see, it is extremely thin. You can see your own pleats. That's why the running is so fast. The interaction is reduced, the running speed increases rapidly. Okay, so thank you so much, volunteers. Any questions you have here? I
Thank
think
you
we
so
have done.
much, Mayuresh sir,
Thank
for
you.
the very interesting and indulging activity as well as an extremely insightful session. The chat box is open for the participants to enter their queries. Uh, let's begin with the Q&A session. I would like to invite Ms. Riya Navalkar from the Department of Life Sciences and Mr. Anurag from the Department of Chemistry to conduct the Q&A session.
Thank you, Sonia. So we have a question from Suchishmita Ghoshal from KC College.
Yeah.
Can we use this method to analyze steroidal hormones?
Yes, even steroidal hormones can be analyzed by this method. What is very necessary is that steroidal hormones, they are not properly water soluble. Okay, so many of the hormones, especially if you go for cytosterolic methods, hormones, you need phases to be different. They are soluble in methanol and ethanol, so you need more compounds, chemicals for it. But yes, steroidal hormones can be assayed through this method also. Any other question? I think Arshana Sonia, I can read it, just a moment.
So
The
the
con
next question.
Yeah, Ria, continue please.
So the next question is from Archana Soni. I think she's from KC College. The cornstarch stationary phase melts away after keeping some time in water. Is there any other stationary phase that we can use?
One, it does not melt away, it dissolves in water. Okay, so it's not just melting, it's dissolving. And we are using cornstarch because you are doing the activity at home. Okay, if you were doing the same activity in a laboratory, the compound that we would have been using is silica gel G. Okay, silica gel G does not interact with water at all. It does not like water that much. Okay, so silica gel G ke banane ke liye, you, instead of what we did, we had water and cornstarch, mixed it up. It becomes hard. Okay, mixed it up. For silica gel G, you use chloroform. Okay, so once the dipping thing is done, once your plate is dry, chloroform is out and it does not react with water at all. So this dissolving part does happen in manual plates. Some amount of stationary phase is lost many times, but it does not simply dissolve away. So yeah, there are many other options. You have cellulase or cellulose as an option. You have CMC as an option for making homemade plates, and different types of silica for sure. I think that answers your question. Any other ones?
So we have a
Suchit?
question from
Yeah.
Urvi. Do we have to activate the slides while using cornstarch like we do for silica and chloroform?
You don't need to actually activate slides with cornstarch, because remember, cornstarch slides are not going to survive. Okay, it's a very make it and do it kind of an activity, so activation is not required. Okay, for silica and such activations, for silica and chloroform activity, you need to activate the slides, because by natural process, okay, we don't get fully pure compounds and you have a lot of humidity settling that can create interactions of hydrogen bonding. Okay, and in simple words, water can, it becomes a bit, there is a bit of humidity on the plate that can interfere with your results a lot. So that, to remove this thing, you need to activate the plates. In case of cornstarch, it's just make it now, use it now, so no activation is not required here. Okay, I think there is one question that you missed. Sushishmita is asking, the way it's used in homeopathy and Ayurveda, can it be used for allopathic medicine? Yes, the example that I gave of acetaminophen or paracetamol, okay, crocin, TLC, HPTLC especially, is one of the most important methods, along with HPLC, which is used in allopathic medicine standardization also. In simple words, to make a medicine, you need these systems. So yes, even allopathic medicine, it is used in a lot. It is used in very high quantities to understand what the medicine does inside your body, inside the human body. Okay, and what does the body do on the medicine also. So all this analysis ke liye you need HPTLC, TLC and HPLC systems. Any else?
No, sir. Thank you so much.
Okay,
Yeah.
I think that should conclude with the Q&A. Volunteers, can you please post? I'll just post the feedback form here.
Yes, sir. Thank you so much, sir, for answering all the questions patiently and thoroughly. The feedback link is in the chat box right now for the participants. Please do fill it at the earliest possible. Um, Now, I would like to invite Miss.
Just a moment.
Yes, sir.
Sonia, there is one more thing that needs to be put on chat box. Just give me a small moment.
Yeah, sure, sir.
Yeah, what I'm putting on the chat box, participants, is the post session activity. It is the same same kind of a form that you filled before the chromatography workshop. Okay, before the start of the chromatography workshop, I'm dropping in the form again now as a post session activity. You are all requested to just attempt the form. Okay, again you can see the link here. I'll just launch it once again. Yeah, post session activity form has been launched on your chat box. You are requested to attempt that form once again. It's again just 10-12 questions, very simple ones. I'm quite sure you will be able to do more effectively this time also. So just do attempt that also, that form. Yes, I think there is one more question in the chat box. Is there any temperature range for this method to be completed successfully? Yeah, for temperature range, remember, for any method, not just this, temperature range will depend upon the compound that you are dealing with. Okay, if your compound is thermostable, then temperature does not play a much bigger role as such, as long as you are okay with the working temperature. If the compound is thermosensitive, okay, sensitive to temperature, then yes, temperature does play a lot of role. Okay, similarly, if your compound is light sensitive, photosensitive, then the whole reaction actually, the whole chromatography needs to be done in sodium light, so not in natural light, and different light settings or under dark. So yes, temperature, light also plays role with this technique. Per se depends upon the compound of interest that you are trying to work with. An example I can give for you is a compound called as gallic acid. Okay, gallic acid is what you get from Triphala churna and all these compounds. Very good compound, very medicinally potent, but it is light sensitive. Now this is the reason many of the, you have allopathic medicine bottles and Ayurvedic medicine bottles which come in black bottles, okay, coated bottles. Okay, that is because it can react with light, and that can create a lot of problem as such. It will degrade the compound ready base. So yes, that's, I think, your answer for this. There is a question on the chat box. It is directed to me, so others cannot see it. I'll just read it out. Sir, can you give one example of quantitative analysis by chromatography? Yeah, for quantitative analysis, I think you must have seen on slide the example we discussed of Arkavati and Lavangavati. Okay, so what has been done? The plate is developed. Okay, after development, along with the marker, along with my formulation, I have a standard which runs along with it. Okay, now standard ends up giving me a certain amount of area, a certain amount of quantity that I know कि मेरे 10 ppm standard will have that much amount of quantity. Okay, now when the same band, that same RF is also seen in my sample, one thing is done, that I know this band here from my RF, from my sample, is piperine. Okay, one part is cleared. So qualitative is done. Now using densitometric scanning, you saw those peaks and everything. Using that scanning, I can measure the area that that band is covering. The intensity of that band can be measured out. Okay, and then it's just plain cross multiplication. In simple terms, you can just cross multiply, compare it with the area that the standard band gave, okay, against what band I have received, and yes, I can quantitate the marker very successfully. If I want to still go into a very precise quantitation, then you need to follow a process called as validation, which is a completely different chapter in itself. But yes, you can quantitate using chromatography right up till picograms, no issues at all. The methods can be developed which are that sensitive easily. Okay, I think Neelam, I've answered your question. Anurag, can you please check the post-session activity responses if they have started?
So the responses are coming in smoothly, sir.
Yeah,
Uh,
that's good.
yes,
Any other
volunteer
question?
team, can I say something?
Yes, yes, please, ma'am. Please, ma'am.
Okay, so I was there throughout this session, and to all the students who are here, and faculty members, and even some postgraduate students, I think this form filling activity that we are asking you to do is simply because to check for yourself whether whatever were your understanding or ideas before we started with the workshop, whether you have got any sufficient information from which you can have a better understanding now. And so please bear with us when we ask you to fill up few forms, and it is for us as well as for you to understand the impact or the usefulness of these sessions that are being conducted by our teachers. That's the first thing. And I'm sure those who had attended it from the day one, and now day two, I'm sure you must have understood that it is getting more and more interesting. And so the day three, please do not miss it. It is not always for the certificate that we do things, but we also do things for enjoyment. And if you enjoy science, I think that is what makes you happy at the end of the day. So we have Charulata Chaturvedi ma'am tomorrow, and she's going to be having a complete hands-on session for you all. She's going to show you some very interesting magical things that we can do with chromatography. So I sincerely request each one of you to be on time so that we get more time to do hands-on activity tomorrow. Wonderful session. I cannot praise my own people, so but I can still say that wonderful session, Dr. Mayuresh.
Thank
I
you, ma'am.
learned so many other things, and I revisited my chromatography techniques. So thank you for that. Thank you all the participants, and yes, all my volunteers. Okay, we are really happy that you are working round the clock. So over to you, volunteers, for a formal vote of thanks. Thank you so much.
Thank Thank you so much, Sagarika ma'am, for always being a source of motivation and support. Thank you, Moiresh sir, for the amazing session. The the feedback link and the link for the post activity session have been posted in the chat box. Please go do look at the chat box. The link will be open till 9 p.m. tonight. So please fill it at the earliest. I would like to invite Miss Urvi Achyutan from Department of Chemistry to convey the vote of thanks.
Good evening to all present. I hope you all enjoyed the day 2 of the Bandit Up workshop organized by the Department of Life Sciences and Department of Chemistry. It is my honor and privilege to give a vote of thanks to all those who helped make this happen. I'd like to thank the principal, Dr. Hemlata Bagla, for giving us the opportunity to organize this webinar. I'd also like to thank Dr. Sagrika Damle, Head of Department Life Sciences, for being the pillar of the webinar. I'd like to thank our guest speaker for today, Dr. Mayuresh Joshi, for all the valuable information he shared with us and for letting us know that we can make TLC slides even at home. I'd like to thank the participants, faculty, undergraduate, and postgraduate students present. This event would not be possible without you. I must not forget to thank the volunteers and the student teams who contributed to organizing this webinar. Thank you.
Thank you so much, Urvi. Thank you all for being a part of the day 2 of our webinar. Hope to see you in same strength tomorrow for an amazing day. The feedback link will again be posted in the chat box. Please fill it at the earliest. Thank you so much.